This is problem 853. So the problem consists in heating air with a steam condenser. So the main idea it is that we have a tube, and this tube it is 5 meters long and has a diameter of 50 millimeters, and steam is condensing on the surface. So there is a steam condensing here, because of the condensation happens as a constant temperature. So this is a problem with constant temperature. So the temperature on the surface is going to be equal to 100 C, and the air is coming at 20 C, and the problem requires to know what is the temperature of the fluid at the outlet, the mean temperature of the fluid at the outlet. Okay, the first thing that we have to do it is to find out the properties of the air at the temperature inside the tube, like an average of the temperature. So what we are going to do on the first place it is find out what is the mean temperature of the air inside the pipe. So we know that the temperature at the inlet is 20, so we have one value, but we don't know the temperature of the air at the outlet, so we have to guess. So if the temperature on the surface it is 100, so it should be less than 100, but the maximum will be 100, so I will put 100 as a guess. So remember, this is a guess value, and the average then it will be the sum of the two temperatures divided by 2, so that's going to be 60 degrees C. So that's an estimation of the mean temperature, and with that one we can go to the table in the book in the appendix and find out the values. So I already did, and I found that the specific heat it is equal to 1008 joules per kilogram Kelvin. The viscosity it is equal to 198.8 10 to the minus 7 newtons second per square meter. The conductivity of the air it is 0.0285 watts per meter Kelvin, and Prandtl it is equal to 0.703, which is typical for the air. So now that we have the properties of the air, the first thing is to determine if the fluid it is turbulent, if it's turbulent, or if it's laminar, and also if it's fully developed. So let's do the second part of the problem. So part B is computing the Reynolds number. So Reynolds number, Reynolds D, because it's a pipe, it is equal to 4 times the mass flow rate divided by pi multiplied by the diameter and the viscosity. So this is 4 multiplied by the mass flow rate, which is 0.01 kilograms per second, and divided by pi, and the diameter it is 50 millimeters, so 0.50, and mu, which is 198.8 10 to the minus 7. So Reynolds in this case it is going to be equal to 12,809. So that's going to be Reynolds D. Therefore it is bigger, so this is bigger than 2,300, so that implies that the flow is turbulent. Okay, now that we know that the fluid is turbulent, we have to compute H. So the last part, or part C of the problem, is to compute H. Okay, we need to use some of the correlations. So the correlation that we are going to use is, of course, the one corresponding to turbulent flow. So nozzle D, it is equal to 0.023 Reynolds D to the 4.5 and Prandtl to the 0.4. So the fluid here, it is heating up, so that's why we choose the exponent of Prandtl equal to 0.4. If it's cooling down, it will be 0.3. So we already compute the value of Reynolds, and we know Prandtl from the properties of the fluid. So we can just replace, so this is 0.023 Reynolds, and Reynolds is 12,809 to the 4/5, Prandtl, which is 0.703 to the 0.4. So finally, nozzle, it is equal to 38.6. But remember that nozzle number, nozzle D, because it's based on the diameter, it is equal to H average multiplied by D divided by K. So we can solve here for H, and so H it is equal to nozzle D multiplied by K and divided by D. So if we put the proper values, we will get that H it is equal to 21.9 watts per square meter Kelvin. Okay, now that we know the value of H, we should be able to compute the temperature in the outlet. So let's move into the next page. So what do we know so far? We know that the fluid, it is turbulent, that it is fully developed, and that Ts, the temperature at the surface, it is equal to a constant. So if we want to make a drawing of the temperature, we know that if the temperature, it is constant, so this is X and this is the temperature, so the temperature in the constant in the surface is going to be a constant, so this is Ts, and the temperature in the pipe, it will be starting at some value, it is heating up, and it is going to be exponential, so that's delta T at the inlet, and that's going to be delta T at the outlet. And the temperature distribution, it is given by the following equation. Delta T at the outlet divided delta T at the inlet is equal to the exponential of minus PL multiplied by H divided by M dot Cp. So this is for the case when we are evaluating at the outlet. Okay, so we have that delta T at the outlet, it is equal to Ts minus the mean temperature of the outlet divided by Ts minus the mean temperature at the inlet. So this is equal to e to the P is the perimeter, so it is going to be minus the perimeter is equal to pi multiplied by the diameter times the length times H average and divided by the mass flow rate and the specific heat. So if we solve for the temperature at the outlet from this equation. So we are going to have that Ts minus the mean temperature of the outlet, it is equal to Ts minus the mean temperature at the inlet multiplied by e to the minus the same factor pi dLH and divided by mass flow rate multiplied by the specific heat. So finally we can solve for the mean temperature of the outlet. So this is going to be equal to the temperature on the surface. So because this is negative, so we have to move it to the other side. So Ts is positive and the last term becomes negative. Ts minus Tmi multiplied by the exponential of minus P dLH divided by the mass flow rate multiplied by the specific heat. And if we replace the values, that's going to give us a value of 85.6 C, Celsius degrees. So we initially, for computing the properties, made a guess of 100. Of course, wasn't going to be 100 because that's the upper limit. But it was close, at least for the properties. If we want to check or improve the results, so we have to recompute the properties of the air at 85.6 and iterate a second time. Okay, this is the temperature at the outlet. Now if we want to compute the total heat transfer, so we can do a balance of energy. So we have energy at the inlet and energy at the outlet. So Q, the total heat rate, it is going to be equal to the mass flow rate, which is the same for the inlet and the outlet, multiplied by the specific heat, and the delta of the difference of the temperatures, of the mean temperatures at the outlet and at the inlet. So if we replace for the proper values, this is going to give us 660 watts.